Hey there, everybody. Welcome back. We're going to start chapter 14 in Calculus 3 in the 11th edition of the Anton book. In this section, we're starting to cover multiple integrals. We've done partial derivatives and derivatives in any direction. Now it's time to start looking at doing integration. So like the way we did it for one dimension, the integral from a to b of f of x dx, we did this limit as n goes to infinity of the function times delta x from I equals 1 to n. And we had this function xi evaluated between the blocks xi minus 1 to xi. So we'd have some grid, and we're going along up to n, xi minus 1, xi, and xi star was within it. And we were doing blocks. We're basically integrating blocks, doing a good old Riemann sum. This idea scales up nicely to multiple dimensions. We're going to let r equal from a to b. That's our x component. And it's going to be a square region. We're going to make it rectangular, at least not square, but rectangular. Y will go from c to d, so that x is between a and b, and y is between c and d. And we'll let f of x, y equals z. And we want it to be greater than 0 over the whole region. At least for now, it makes sense because we're doing the area kind of thing. So we're going to treat it like that. We could break the region up, the region R up into parts. I'm going to do x goes into m parts and y goes into n parts. I don't want the same letters, so we could have different limits. Which means delta x is going to be b minus a over m. That's the width. If we break it up into m parts, and delta y will be d minus c over n. And you can kind of see what's going on. From a to b, we're coming along like this. From c to d, we're coming like this. We have some region square in the middle, wherever we're at. This is the xi minus 1 xi and yi minus 1 to yi box right here. And we are finding the volume of this region going up to the surface. Okay, so we're finding the volume of the air, the volume under the curve. So it's not area under the curve anymore, it's volume under the curve. But the region down in the XY plane is just rectangular. We're going to leave it as such for now. We'll change that in 14.2. So delta A, I'm going to call it delta X times delta Y. That'll be the area of the small little rectangle. The volume is the area under the curve for each rectangular parallel pipette. So the volume of box MN will be f of x. I should say f of x I, yi. So we can, like we had our limits up here, we can write the volume as this right here is an approximation. And if we do the limit as m and n go to infinity, this will switch to an integral. So we have the integral of f of xy over the dA of the region R is the limit as m goes to infinity, n goes to infinity, of f of xi, yi, delta A, and each of the I equals 1 to m and j equals 1 to n. We've just basically upscaled the idea of the Riemann sum. And let's take a look at how the integrals work. So basic integral properties apply. If we take the integral over a region, I should have an R in there and don't. If I have the sum of two functions being integrated, I can break it up as the integral of two functions, or the double integral of two functions. When we have two integrals, it's called the double integral. When we have three, it's the triple integral. We also have, when there is a constant times the function, we can pull the constant out. That's good. If f of xy is greater than or equal to g of xy for all xy in that region R, then the integral of f of xy is greater than the integral of g of xy. Seems straightforward, makes sense. But how do we choose to integrate this? So we got x's and y's. So we got two strategies we can go with. We can hold xi fixed and integrate across y first. So we're doing it with respect to y. So we kind of got like an integral of f of xi, and then we're integrating y dy just along a single block for xi. We'll go from c to d. The results will be a function that no longer has y in it. It'll just have x. So we call it a of x. And so the integral of a to b of a of x dx, we plug a of x inside, and we see that the double integral is a to b, c to d, f of xy, dy dx. These are called iterated integrals. And notice that we did dy first, y first, and it's on the inside. So inside first, work outwards. Okay. If we decide to go along the other way, integrate with respect to x first, then when we integrate the integral with respect to x, there's just a function of y remaining. So we'll make this, I'll call this function b. B of y is the integral where we integrate out x for the function from a to b. For that single yi block, then when we plug that in, we do the full integral. We see that c to d, a to b, f of x, y, dx, dy. Notice the order has switched. It's different now. We've got dx first, then dy. And for a rectangular region, there's a good guy named Fubini. Back in 1907, he showed that we can change the order of integration for a rectangular region. It doesn't cost us anything. So we go a to b, c to d, dy dx, or c to d, a to b, dx dy. That'll be it for the first video for 14.1. Peace.